Yeah, I'm Sandra, and I've been doing reverse engineering mostly, and also binary exploitation. So today I'll be giving you an introduction into binary exploitation, and since it's five already, I think we can dive into it. Also, if I am too fast, or if you can't catch up with my speed or my accent, please put it in the chat, and Simran will let me know. And the moderator will let me know if I'm too fast. Okay. And also, you can stop me if you have any questions. So let's dive into it, right? We'll be going through the basics of like you will have to start with analyzing a code and a little bit of reverse engineering. But at the end, you'll know what exploitation is and how it impacts our daily interaction with computers, and how exploitation is the extent of disruption that exploitation can cause in the cyber community. So uh, to start with, let me start with an example that is a Morris one. So, if you had attended the intro to CTF's talk initially, like that was our first talk, and if you had attended that, you must have already heard about the Morris worm. So, the Morris worm, what is it? It was, yeah, the first worm ever to infect computers, and it was built by a university student whose name was Robert Morris, and the worm was named after him. So, was that his intention? No, it was just a science experiment that went wrong. Just like you did something, but the impact was so huge and hard to remove. So, what Morris was trying to build was he just built a small program to highlight some security flaws in the Unix system, but a small error or an unintended bug, you can call it, caused a significant amount of disruption because every seventh time it executed, it replicated itself. And that was not intended, but that's what it did. And that just made it all the more difficult to remove such a bug. It was supposed to exploit the system, but it was not supposed to spread itself, right? So that's what it did, and it was not supposed to happen. So it targeted Unix systems. It did a simple password cracking locally. It exploited a bug in the finger daemon. It exploited a bug in the sendmail function, the PHP sendmail function, and it did all of this. And if any of this succeeded, it basically replicated itself. So, with that example, I think we can move on to the agenda of binary exploitation. Why I showed you that example is because I wanted you to understand that such a small bug, the impact that it had was that it affected 60,000 computers. This is the approximate statistics that it affected 60,000 computers around the world. Such a small unintended bug. So, I wanted to start with that example to just show you the gravity of the issue. So we'll be going through what is binary exploitation. We'll understand what the stack is, how to approach an executable, how you spawn a shell, and then reading assembly and understanding the code to in order to exploit the bug that we have in the program. And then we'll go to a live demo, and then we'll have an FAQ session, Q&A session. Sorry. So what is binary exploitation? That's what we're here to know. So this is a 5 or 6 line code, and you might think this cannot create a lot of issues, but it can actually do a lot of things. And I want you all to read the code right now. It's a very simple one. It initializes a check variable, which is initialized to the value 0x04030201, which is a hex value, and then it declares a character array, also a string, uh, and the next it just prints out a string. It gets a string of length 25. It checks the check variable, uh, which is which is kind of suspicious because it assigns the check variable with 0x04030201, and then it checks it with another value. So uh, that happens, and then it calls a system function. Anything suspicious? Sure, but we have to find out where. So, Simran, can you post the code in the chat if you haven't? Okay. And moving on, what does a system call do here? There's a system function called here, and what does it do? It's a library function that basically calls uh, it basically executes the function that is given inside the codes in the system function. So the string that is given inside the system function will be a Linux command which can be executed. So executing this on a different system can actually give you shell to the other system, and you can access the files, and the file system to the other machine will be accessible to you, and you can do whatever you want with it, which is kind of a bad thing to happen, right? So, so we know that here our goal is to finally execute the slash bin slash sh, and that's how we exploit this program. So, yeah, we found the bug. Binary exploitation is thus the exploration of such bugs to gain higher privileges on remote systems. So you have this code running on a different system, and you'll get if you are successful in exploiting these bugs on a different system, you basically get access to the file system of that program of that machine. And binary exploitation involves taking advantage of such a bug or a vulnerability in order to cause such unintended or unanticipated behavior in the problem. So right now we've just found the bug, and so how to approach such a bug, how to approach an executable when you get it. So you first reverse the binary and analyze it, and then you have found the bug, found the vulnerability now, right? And then you have to trigger the bug somehow. And then for that you have to craft an exploit, and you finally spawn a shell, and that's when you know, yeah, you've got it. Next we'll to exploit the bug. Our approach is to exploit the bug, right? In the next slide we'll be going through stats. When you execute a program, you have this memory layout in which the entire program is stored, and that memory layout will be used to execute the program, and the variables used by the program and everything will be stored in there. So this is the memory layout starting with the stack at the top and the text section at the bottom. And you have the data section right above the text section, BSS, heap, and the shared libraries. We'll tell you what all that is for. So at the bottom, you have the dot text section where the code of the program, the assembly instruction, the instructions that are there, the machine code that is stored in the dot text section from where each of the program code is executed. And above it, you have the initialized data. That is the dot data section, where in the previous program you have int check initialized to the value 0x04, 030, 0201, and such data will be stored in the dot data section. Suppose you have another variable. From the previous example, you have the intruder variable, which is declared but not initialized. So such uninitialized variables are stored in the BSS section. Then you have the heap, where the runtime variables are stored, and then you have the stack, which stores the instruction pointers, the pointers that are required for the program to function in a systematic manner. Also, the variables that are immediately used to call functions and all that will be stored on the stack, and the stack grows from the top to the bottom. So in the previous slide, you can see I've marked the address of the stack to be 0xFFF, which is the highest address, and the text section to be at 0x000, which is the lowest address. Okay, so we have these addresses, and so you know that. So now we know that the stack grows from the top to the bottom, and this stack, what points to the top of the stack is called the RSP register. It is the register stack pointer, which which always points to the top of the stack. And then we have the RBP register. It always points to the bottom of the stack. Register base pointer. And RSP is updated during every push and a pop operation. And RSP is incremented on push. RSP is also decremented when a pop instruction is executed. So, what RSP stands for in a 64-bit is the equivalent of an ESP register in a 32-bit system. So, and next we have, so now we have come to a conclusion of what the stack segment does. So the stack segment is basically used to store all the local variables that is used in passing the arguments to the function and along with the return address of the instruction which is to be executed after the function call is over. Uh, so these are all the stuff that I explained before. Like it stores the real-time variables. Like when you have a function being called, all the arguments to that function will be stored on the stack and then passed to the function. That's also if you are not speaking, can you just mute yourself? All the attendees. Okay, thank you. Okay, now we have the 32-bit stack layout. So, like I mentioned here, uh, the 64-bit system, there are 64-bit systems and 32-bit systems, right? So, in the 32-bit system, this is the stack layout. So uh, you have the registers. You can see here, as you can see here, the registers are marked as EBP and EIP and ESP and all that. So why this is because there's a difference between the 64-bit registers and the 32-bit registers. The 64-bit registers are 64 bits wide and the 32-bit registers are 32 bits wide. So, and every time you allocate a variable in 32-bit systems, it increments or decrements the memory by 4 bytes. And in 64-bit systems, it increments or decrements similarly by 8 bytes. So you can see it here. I guess it's decrementing by 4 here. It's incrementing by 4 here every time. It's 4, 8, 12, and 16. Whereas in 64-bit stack layout, it is 8, 16, and then 24, and similarly decremented. So next we'll be moving on to the function calling conventions. What happens when a function is called in, what happens to the stack with respect to when a function is called. Next we have, yeah, so we'll be looking at that. So first we have, so whenever a program is called, whenever you execute a program, the first thing that is called is the main function. And with respect to the main function, starting with the main function, we'll be explaining what are the different changes that happens with the stack. So first we have when a main function is called, first, whenever any function is called, what happens is the call instruction basically saves the address of the RIP. RIP is the register that points to the next instruction to be executed by the program. So if I have the RIP, if I'm currently executing the push RBP instruction, which is this one, uh, the EIP will be pointing to move RBP comma RSP. So that's the value of RIP here. So RIP is first pushed to the stack when a new function is called. The call main, that function basically pushes the RIP value into the stack. We'll understand why in the future. So and next we have push RBP and move RBP comma RSP instructions. So these two instructions are called the function prologue, and these two instructions are compulsorily there whenever you compile a program. These two instructions are the first two instructions to start any function, and they are called the function epilogue. Sorry, prologue. And the last three instructions that you see here, uh, specifically move RBP comma RSP, pop RBP, and the ret. These three instructions are called the function epilogue, and they are also compulsory in every function. As you can see here, we have the push RBP comma RSP when the main is called, and when the test is called, we have push RBP and move RBP comma RSP, and the epilogue here. So we'll be going step by step through all that. So I just wanted to tell you that what function epilogue and prologue are. So once the push RBP is done, you might all know what push instruction does. It basically pushes the value of the RBP register into the stack. RBP always points to the top bottom of the stack or the bottom of the function stack. and it is pushed to the stack so that you know, okay, this is the bottom of the stack. So when I assign any variables or anything to this, assign anything or anything to this function, in this function, it has to be assigned below my function pointer. So the function basically starts at RBP, the point on the stack where RBP is stored. And when move RBP comma RSP happens, what happens is the RSP, the stack pointer, is signaled like, hey RSP. So this is where you have, the RBP is telling the RSP, this is where you have to start storing the variables from now on. I am the top of this function, and you can store all my variables below me. So that's sort of like the other meaning to it. So so you move the value of RSP to RBP, and then we have sub RSP comma 4. So what that does is, as you all know, like the stack grows from the top to the bottom, and when you subtract 4 values from RSP, this happens. The RSP pointer gets moved 4 bytes towards the bottom of the stack. So the stack basically grows to the bottom, and it has added four bytes of space into the stack. And now the next variable will be stored below this 4 bytes. So what is happening next? Next, we jump straight into the call function, for call function one, which is the test function. And why I have put push RIP in brackets is just to let you know that that is what is happening. When you call a function, it automatically pushes the RIP value to the stack. And yeah, you can see on the stack the RIP value is pushed. And you can see that next, when the next instruction is executed, it has pushed the RBP value, that is push RBP, pushed the value of RBP to the top of the stack. So what happened is, it it saved the, it is again telling the computer, okay, hey stack, this is the new top of the function. The old RBP, what this RBP contains is the base that we stored earlier, right? So this is the value of RBP, and that value is pushed here, so that when we return to the function, we know that, okay, the old function's base pointer is here. And we don't want the RBP to be wandering around not knowing what my earlier value was. So we have to go back to the previous function, and the computer knows it, and we have to tell the RBP, okay, that this value has to be stored here, so that I know where to go back when this function is over. So after that, the RBP is pushed, and then we tell the RSP, okay, hey RSP, we are going to the next function, and now the next set of variables have to be stored below me, so that I know the variables of this function are stored specifically with respect to my this function's top. Okay, and next we have a couple of any instructions that you want to imagine. We suppose did a push of two variables, and all those variables are stored here. You can just imagine that there are some variables here, and you can imagine whatever instructions have been executed here. So, and then we move on to the function epilogue. So what happens here is, it moves RBP to the RSP variable. So it is basically trying to, the end of the function, when it comes to the end of the function, you know, okay, this function's over, and you have to delete this stack frame. This stack frame does not mean anything to you anymore, because this function is over. So we're trying to delete the stack. So what happens is, it moves the RBP value and the RSP value to the previous RBP value. And so you have both RSP and RBP at the same position now. And what will happen next? Now you are completely removing the value of RBP to the, you're popping the RBP value. So what pop does is, it removes the value at the top of the stack and saves it to the register that is mentioned right after it. So here you have the RBP, which points to this, the first RBP on the stack. So when you pop it, the value of the old RBP is saved to the RBP, right? Like again saved to the RBP. So we have the RBP there, RBP pointing back to the old RBP. So the RBP goes back to its original position after that instruction is executed. Next, you have the ret function. So I haven't told you so far, but the ret function, what it does is it pops the RIP, pops the value at the top of the stack into the RIP register. RIP is the register, as I told you before, the register that holds the pointer to the instruction that is to be executed next in the program. So ret is equal to pop RIP. So it's equivalent to pop RIP instruction. And you have, like I mentioned before, the RIP was stored here in order to go back to the next function. So we stored the RIP from call function 1, right? So at this position, the RIP should be pointing to this function, which is the next instruction in the main. So this is the value that was stored to the RIP and was pushed onto the stack. So this value, when popped and popped to the RIP, it gives back the position of instruction to this one. So the next instruction we know is to be executed is move RBP, RSP. And as that happens, the base pointer and the stack pointer is the same now. And now we know like it's the same thing over again. It moves RBP, RSP. It's trying to delete the stack frame again because the main is exiting. And yeah, it pops RBP, and saves it to the old RBP value, which we don't want to know because main is our we started with the main and we'll end it with the main, and we return that is pop EIP. We've popped the EIP from the stack, and the stack is basically cleared. So that's how the stack grows and clears itself when a program is executed. So at this point, does anyone have any doubts? Okay, I guess not. So I'll move on. If you have it, you can post in the chat and they'll be replied to. Next, we let's just summarize what we understood from it. So the two main things I wanted to focus on was the ret instruction and the call instruction. The ret instruction is equivalent to pop RIP, which saves to the RIP register the address that is on top of the stack. That is the next instruction. RIP always has the next instruction, and that will be on the top of the stack, and that will be stored into the RIP register. And call instruction pushes RIP onto the stack. Okay, so now we'll be slowly moving back to our challenge, and we'll be understanding why do we have to spawn a shell, right? So how do we exploit the bug we found? We saw in the code that uh, it is a buggy one, so I put a bug there. And so looking at the code, we know that a shell is being called. So it's called spawning a shell. If you get a shell on another system, you know how to exploit it. You know, you just have to figure out how to spawn the shell, and that's the vulnerability. And if you are successfully exploiting that bug, then you have exploited it. So from
Sorry,
this,
Sandra, just on the slide, maybe just check if everybody understood what the bug is or
yeah, okay,
what
yeah,
is the exploitation.
yeah, okay, that was my next question. So, uh, has anyone understood what the bug is yet? Because next I'll be disclosing the bug to you. So I want to know if anybody found out what the actual exploitable bug here is.
I think
You can
I
answer that.
think
Yeah, go ahead. Sorry.
I can't hear anyone. Is anyone speaking?
Is it attempting to read 25 characters into a 20-character array?
Yeah, so that is the bug here. So there is a 5 bytes overflow in this program where intruder is assigned only 20 bytes, whereas fgetters is taking 25. So there is 20 spaces assigned for intruder, but it's taking more than that and it does not know where to store the extra 5. So it overflows the check variable that is assigned right above it, and you get an overflow and you can change the value of check in that way. So fgetters reads 25 bytes, but the allocated space is 20 bytes. The 5 bytes overflows and allocates itself into the check variable, and hence you can override the check variable with 0x cafe babe. We'll be doing that manually, and I'll show you how it's done properly. And here we have a stack representation of what happens in the program. So here you have the intruder variable. Here you have the intruder variable. So it's assigned 20 bytes, but the check variable is assigned with 0x04030201 right above the intruder variable. So when you overflow the intruder, it gets overflowed into the check variable. So that's what's happening in this program. And yeah, so our input can be something like Python space minus C print of a slash 20, a star 20, a 20 times, and then overflow it with 0x cafe babe. You add like 5 extra bytes because fgetters is taking 5 more, and then you can overflow it. This is what ideally should be the solution, but there is a very small alteration to this, which we'll come across during the live demo. So this string should be piped to the program and you will get the shell. So next we have a short quiz, and for that we'll be using Slido. So you can all log into Slido to see the questions. So the first question is, uh, did you get the Slido? Okay, the Slido slide number is, you have to log into slido.com and then enter hashtag E378 to get the questions. And if you find the questions there, you can answer it and then we'll know. We've got one response. Okay, we've got 6 now, 7. Okay, I think almost we've got enough responses, and so yeah, everyone is right. So the top of the stack is represented by the RSP register, and the bottom of the stack is pointed to by the RBP register. So we have the next question. What function does the call instruction perform on the stack? So you can all respond now. Okay, I guess that's it then. Yeah, it's the answer is push RIP. So I had explained earlier, when a function call instruction is executed, push RIP is the instruction that happens on the stack. It pushes the RIP so that it knows when you exit the function where to go back in the main function, if you remember. Okay, next. The next question is function of EIP, RIP. What is the function of the RIP register in the registers? Okay, to clear things out, RIP does not point to the top of the stack, and yeah, the rest are correct. It points to the next instruction. It RIP always points to the instruction that it has to execute next, and not the return value of the instruction before. That I think might have been a little confusing. Okay, so it always points to the next instruction. The next question is, what is the function of the ret instruction? Okay, yeah, everyone is right. For this one, I want one of you to speak up and tell me, like, when a new function is called, how is the stack frame altered? It's not a one-word answer. So I would like one of you to speak up, unmute and talk.
I can try. Um, the
Yeah.
stack will grow downwards.
Yeah, but also can you mention about the registers, like what all are pushed and how it grows? When a function, like the epilogue and the prologue part. Only if you understood it, it's fine.
I can give it a try. So the first thing that happens when we call a function is we push RIP, or the previous RIP, to be able to go back to the, like after we return from the function, to be able to go back to the next instruction that was supposed to be executed. And then next, as you mentioned, we have.
Sorry for interrupting. Maybe it also is easier for everyone if the slide also shows the stack. Sandra, can you just go back and show a stack picture? Then you can see it again.
I'm guessing it's this one. Yeah.
Yep. So we store RIP in the stack, or we push RIP into the stack, and then we have the prologue, which pushes RBP, and then moves RSP to RBP.
Yeah. Okay, that's good. Okay, thank you.
Yeah, actually, if there are really beginners who haven't seen stack before till now, please don't be worried, because it really takes so much time and so many times looking at it to actually get the right flow and what it does. So yeah, please don't be intimidated if you don't understand how it functions. And yeah, please ask if you have questions and if you want to, yeah, if something is not clear.
Question?
Yeah, sure. If you have any
So
questions, let's clear them up.
can I see the stack again? Sorry, it's
Okay.
confusing.
I should probably just. Okay, I think this one's good enough.
Oh, so in the instruction, there's a subtract instruction.
Yeah.
Subtract RSP4. So
Yeah.
I get that by subtracting, you're subtracting the high address towards the low one. So the stack moves from high address to low, right?
Yeah, so in a diagram that I showed before, the top of the stack was marked with 0xFFF, right? And the bottom was marked with 0xF000. So I just wanted to tell you, what I tried to tell you was that it always grows from the top to the bottom. So when so if FFF is at the top, so FFF0 will be towards the bottom. And I also told you that the stack grows from the top to the bottom, and that's what that was supposed to be like interconnected. And you, so what you have to understand is that when you add a space to the stack in a function, you have to subtract values. If my RSP is at 10,
Yeah, maybe
I'll
I
have
can also just show that diagram where with the
sure.
minus, yeah, the stack address.
I think this one's good enough.
Okay.
Here you have the RBP, and when you have to add space to the stack, you subtract 8 values. So 8 values will be one block of memory on the stack, and the next 8 will be another, and that's how you assign spaces or values in onto the stack.
Yeah, actually
So
those X, Y, Z are the variables and you are allocating space for that, right?
oh, okay. But like when you why is the address called pop? Like, can you like subtract? I mean, sorry. If you add on to the address by subtracting, then don't you like pop? Does pop mean like adding back to the address?
Pop is a stack specific instruction. So when you subtract, you change the value, you subtract the value inside the register. And when you do pop, it is not dependent on any of the registers. It just stores the value that it pops into a register. Pop only operates on the stack. It pops a value from the stack and stores it to the register. That it's like if you do pop RAX, then the popped value will be stored in the register RAX. And subtract only subtracts the memory address inside the RBP or RSP instruction. Okay.
If I understood it correctly in my previous classes, if you're doing a push, you're actually allocating space in the stack, right? Like for example, if I do a push, I'll get the X, but
Mm,
if it's not there. But if I do a pop, I'm removing that X from there.
yeah, okay. Yeah, you can push a value into the stack and allocate space for that value. And then if you pop it, that allocated space is gone.
Yeah.
Allocated
And
value is gone. Yeah.
yeah, and just to give a a mental picture, the higher you can think of the higher address, Christine, as let's say something like 20, and the lower address is something as 0. So if you're going to be moving from 20 to 0, you'll be subtracting. That's why we're using a
Yeah.
sub. If you're
Yeah.
going to be moving, if you're going to be returning it back to the higher address, then you're going to be adding because you're going to be moving from,
Yeah.
some
Yeah.
an
To
8 to a
remove the
12.
stack frame, to
Yeah.
remove it, you're adding it.
So is there assembly instruction for adding the
Yeah, there is an assembly instruction called add, and we mostly use it for arithmetic operations. But yeah, you can also add addresses to like get to access a variable. You add something from the RIP to access the variable stored at that address with respect to that function.
Plus, I
Oh,
think you also
okay, so
show.
I'll explain it a little clearly now. So you have in this slide you have X, Y, and Z initialized. So your RSP is at Z, right? So when you have like next operation is suppose add RSP uh, X add X comma Y. So how it accesses variables is like it'll get the value inside RBP minus 16. All the variables that are accessed inside a function are accessed with respect to the RBP register. That is why we store the base pointer of a register. And so whenever a value is required from that function, you just access it with respect to the top of that stack, that function stack. So you access the variables by calling for RPP minus 8. You store it in a register. You access the variable y, calling it RBP minus 16. You store it in another register, and then you add these two register values. Did that answer your question?
Yeah, thank you.
Yeah, okay. So I think I'll move on.
I have a quick question. I
Yes.
wanted to know, does RBP change? So I know RIP changes as we execute instructions. Does RSP change throughout the
Yeah,
um the-
yeah, it does. Like whenever a value uh, is like pushed, or yeah, whenever a value is pushed onto the stack, RSP increments itself. You don't have to ask it to increment or anything. It is an automatic operation. So whenever something happens to the stack, it will automatically increment and decrement itself.
okay, thanks.
Hi, I have a question related to the bug that you showed in the program. Am
Yeah,
I audible?
yeah, sure, yeah. You are.
Okay. So what I wanted to ask was, intruder is allocated 20 spaces, and if f gets take 25, you said that intruder would overflow into check, right?
Yeah.
So if the stack grows downwards, why would intruder overflow into check since check is above?
Yeah, okay. I was expecting that question. Okay. So, intruder is allocated at let's just say RBP minus 0x16. So it starts storing the variables from 16. Okay, one second. Yeah, okay. Suppose it's stored allocated the space from RBP minus 16 to uh, RBP minus 0. Say let's just say 0 and 0 to 20. So you have the top of the stack, top of that variable address pointing to 20,
Mm-hmm.
and it will actually the values will start assigning from 20 to 0. That's how when memories take when user inputs it, it is stored in little endian format from 20 to 0. So that's from 0 to 20. Yeah, 0 to 20. So it will just grow backwards, and that's how it overflows. So uh, I have a slide for that.
So let's say if the top of the stack is 20 and the bottom is 0, so check gets allocated space from 20 to 16. Is that what you're saying?
Yeah, you have intruder starting here. You have
Okay.
intruder variable starting here, and then it'll you have space from 0 to 20 here, uh, and then 24 here, and then this is very specific to the challenge, so I was just coming to this. So you have like it starts from 0 to the 24 that is here.
Sandra, can you also put the link to the slide on the chat? So if somebody actually wants to move across slides and go back and forward and check stuff, it's easier.
Actually, it's still not a little clear to me. Sorry if I missed something out.
Sorry, what?
I'm saying it's still not clear to me. I don't know if I missed something out, but why would it overflow into check instead of overflowing downwards?
Because that is the space allocated for it. Below that, the stack pointer does not have access to the value, the memory in the stack.
Okay,
So
so if check variable, okay, so if the space is if f gets is taking more than 25, then it would overflow check as well, would it?
yeah,
Okay, okay, now I get it.
yeah, okay. So yeah, after the quiz, we are going into the demo. I'll just share it back 1 second. Okay, so we have our challenge. Is the window visible?
Yeah, it is.
Okay, so our challenge file is the same. Cat. So this is our challenge file. It's the same thing, but it's just a little rearranged. Anyway, so yeah, this is our challenge file, and we'll be exploiting this, the same challenge that we saw. So we run this challenge, and it's called enter the spell to break the charm, which it prints out, and then you give it an input, and it just exits because check has not been modified. So like we said before, what our input our required input is like, it should be something like 20 to fill in the buffer, and then intruder buffer, and then overflow the check variable straight away, right? So if we actually do that, uh, we'll see what happens. Let's see if we can actually exploit it that way. So for that, I'll be using Python space -c. Okay, so this is our crafted input, and because the system is in Little Endian format, most systems are Little Endian format, and because this one is Little Endian, we have to send it in reverse format. As -1. So first BE will be sent, BA will be sent, then FE will be sent, and then CA will be sent. And that's how in Little Endian format, when the program execution happens, that's how variables are taken, like in the reverse order, and it'll only make sense to the computer that way. So I forgot to print it. One second. Okay, so if I print this out, you can see that I got CAFE, are these unidentified characters. So we'll see that while we're dynamically analyzing it. So let's try and see this input passed onto our while dynamically analyzing it. So let's save this input into a file called out.txt, and then yeah, let's dynamically analyze the binary. So we are using GDB PEDA for our demo, and this is for ease of understanding. Okay, so in GDB PEDA, we run a program by simply entering R, and we can run it just like we normally do, and then it'll exit normally. So in order to exploit this, let's analyze the program individually, instruction by instruction. So start. So we have our first instruction, that is push RBP, and then we know what it does, right? So yeah, there is push RBP, move RBP, comma RSP, and then we have subtract RSP, comma 0x20, which is again saving some space in the function, and then as a simple buffer.
Sorry to interrupt. I just wanted to ask sub RSP 0x20. Is it because we have the size of interrupt to be the variable to be 20 bytes, or?
No. This is not the size. No, this is hex 20. So basically, 32 uh, bytes are like saved. 32 bits of space is like allocated on the stack. That is simply as a buffer so that EC overflows are not like unexpected overflows don't happen. So they simply allocate 20. Whenever you compile a program, you can analyze it. So it will simply allocate some space on the stack so that like stupid unintended overflows don't happen.
So it's not a fixed value.
Like a security, like to not allow unintended behavior.
Sure. Okay.
So here we have a load effective address. So what it does is it loads the the value inside this register RIP plus this value, there is some value inside that address. So we'll see what it is. Load effective address actually stores the value inside that address into the RDI register. Let's see what it is using x/s and that address. x/s examines the value inside that memory address in string format and prints it out. So yeah, I hope you can see it now. It has printed the string inside that memory address. So we know what is inside that address, and that is actually the argument to the putS function, which is called next. You load the argument and then you call the function. That's how functions are called in the program. So you do n, and then n will actually n again, and then that will actually print it to the std out. This is the std out output. If there is a lot on the screen and you can't understand, you can ask me, you can stop me and ask, okay? Like GDB Peda gives a lot of dump output, and that is actually supposed to make it easier, but for a beginner, I think it can be a lot. So if you are confused, please stop me. I'll highlight whatever is required, like what I'm explaining at the moment, but if I miss out something, please do tell me. So the putS, this instruction was executed, the execution is over, and it actually printed out the string, enter the spell to break the charm. And so that is done. And then next is the assigning of the variable 0x04030201 to the check variable. So the variable names are not visible because when you compile it, variable names don't get compiled. They're just they're just represented as memory addresses. So into this memory address, that is at 0x rbp minus 0x4, this value is stored. That is the check variables assignment is stored. It is assigned with this value at rbp minus 0x4. You might want to note this down because that will come in handy later. So we do n again to go into the next instruction, and it'll here it's doing std in. So our std in works here. It'll take input from us at fgetS. So here you have fgetS, and if you noticed, as we move to fgetS, these are the three instructions that are actually assigning the arguments to the fgetS function. So first here, this is a memory address again saved into the RAX register, which is that is the memory address of RBP minus 0x20, right? So this again is the next value that here is where the intruder value will start getting stored. And this ESI minus 0x28 is the value for std in. We have used fgetS. I'll show you the code again. We're using fgetS 40 std in and the value intruders of size 20. So here rbp minus 0x20 is the variable intruder. This represents std in, and rax is moved to rdi because rdi is the first argument that all functions take, and rsi is the second argument that all functions normally take. And then okay, now it's waiting for an input, so we give it something like a couple of times and see what happens. So I told you that the intruder starts allocating the values at rbp minus 0x20, right here. Yeah, this is the value where intruder starts getting stored. So intruder, we've just entered our intruder as a couple of A's. So let's see what happens here. Dollar. So at rbp minus 0x20, we have 60, 61, 61, 61, which is the ASCII code of A. character A is represented as 61 in ASCII, and we have a couple of A's that I gave as input, and then there is finally there is a 0A, which stands for new line or next line. So we have actually not overflowed anything. We haven't done anything. Nothing has happened. So next, oh, sorry. Okay. The next instruction after we did the fget here is the compare instruction. We compare the value at 0x cafe at 0x4 RPP minus 0x4 with cafe babe. The comparison here. This comparison is what we're doing here. This compare instruction compares the check variable with 0x cafe babe. And let's see what 0x RBP minus 0x4 has right now. So we have actually overflowed 2 bytes into, we gave 30 characters. So we overflowed it by 2 bytes. Like the check variable now has been overflowed with a new line 0x61 and 0x61, AA and a new line. So next we have to try and make this value what? We have to change it to 0x cafe babe, right? So in our next execution, let's try and do that. So we had crafted an input earlier, right? So that is cat in cat out.txt. We have that input. So let's try and give that to our program. This is how you redirect the input stored in a file into our GDB, and you can analyze it like that. So if you give that, it exited normally. It didn't give you the shell because the value that was checked was not cafe babe. So let's dynamically check it, and for that, let me set a breakpoint right after fgetS. At the compare instruction, let's see what is being compared if I give that input. So I'll run it with our out.txt, and we have break at this instruction, which is at compare. So let's see what is being compared now. It's still 0x04030201, which is what we initialized it with. And that hasn't changed. So something is missing there, right? So what is it? Let's see the with respect to the address of where it's stored, how many bytes are required to overflow this RBP minus 0x4. So the address of RBP minus 0x4 is this one. So you can calculate the value of this address and what is RBP minus 0x20. Okay. So this is the address of RBP minus 0x20. So we have this minus this, and p/d prints in decimal format the address, the prints in decimal format the result of the operation that we're giving. So this is the operation that we are performing now, and it prints the result of it in decimal format. So it is actually having a space of 28 assigned, and we will see why that is happening. So yeah, so let's try giving an input that is 28, and also add cafe babe to it. So it starts at 28, and then you add 0x cafe babe, right? So I make it this, and then after 28 bytes, I'm giving the value that is to be overflowed with, that is cafe babe, and I've saved it in out.txt. So going back to GDB, I run the payload with out.txt. So here you can see that something happened. So after attaching process, it forked a child process, that is, which is the new program, that is slash user slash bin slash dash, which is actually our shell. We got a shell and its process ID is this. So, but we didn't actually get to do anything with the shell. So let's just see if the shell still exists, right? Did it just exit or what happened? It didn't let us do anything. So this shell is process is actually running, but for us to access it, let's see. The PID is this. So yeah, there is actually something running on this shell on this port, and that is this is the process ID, and we have a shell running. No, this is not the shell actually. Okay. Okay, we actually have the shell, but we didn't get to access it. So I'll. Okay, sorry. Okay, we'll actually get the shell in our next try. So with the shell that we got, like we actually executed the shell here, right? That is pretty evident from this, but it exited because I exited the GDB, and that process just exited and it got killed. So yeah, that's why we didn't get it. So sorry about that. So we'll try and redirect it straight and see if we can get the shell. Cat out.txt to cat again. So we'll be passing cat as a command straight to the program again, so that before the shell is exited, we can actually get to execute something in the shell. We can make use of the shell to access the file system, right? So let's do a cat again and then pipe it to our demo challenge. So yay, we've got the shell. We can do whatever we want in the shell. Let's try and cat flag. Yay, we got our flag. So this is how we can also do an ls or whatever. I have a couple of files in here, so you can access any of these files, and that's how you exploit your first program. So get coming back to how why I why there was an extra 8 bits of space that I had to send to the program. I'll be explaining that now. For that, I'll have to share something else. Okay, so this is what I wanted to show you. So here, what happened is intruder started here, and then it actually assigned up to 16 to 20 here, and 24 here, because it has 20 bytes of space assigned to it, but then in 64-bit systems it is justified to the next multiple of 8. So when you have a value that does not require, it still assigns that much space, because for the next variable it will just use the next memory space that is available in the stack. So here check is assigned 8 again, and then intruder, which actually requires only 20, is also assigned 24. So that's how 64-bit systems actually work. And in real time, the theoretical ideas that we have actually don't work, and this is how we fix them. So I just want to show you that part too. So yeah, 8, and we have 24 values assigned for 24 bytes assigned for intruder, and there is 8 assigned for check variable. And I just wanted to show you that yeah, like I said, it's not like we all think. It is different. It's a little different. You have an extra 8 bytes of space assigned, and this you just sent an extra 8 bytes, 8 characters of A's, and then you overflow the check variable. And so that's the end of the demo, and I hope you understood. And if you have any doubts, please ask.
Yeah, sorry, I'm missing something, but why do you need the extra 8 bytes again?
Yeah, okay, I'll explain that again. So in 64-bit systems, whenever you have a value assigned, like if it's an integer or anything, it'll automatically assign 8 variables to it. Let me share it. So you can see this image, right? So it's automatically assigned eight bits at least, so that that's just how it is in 64-bit systems. So when you assign just 20 values here, it automatically just has 4 bits of extra space, and uh, it's always just an 8-bit. 8-bit is the minimum value that can be assigned in a 64-bit system, and it's 4 bytes in a 32-bit system. That's it. So when you have 2 variables, it just added up to 4 and 4, and then you have an 8 bytes of extra space left there. And you have to overflow that to get to the check variable. If you actually analyze the GDB part, you'll understand. I can show it to you. PD main will give you the disassembly. Oh, wait. Okay, yeah, we have PD main, and then you have your RBP stored here, right? I'll just put a breakpoint here like I did before. Um, and I run it with my out.txt that I crafted earlier. And then, yeah, so you know that the check variable is allocated at RBP minus 0x4. Let's start analyzing at RBP minus 0x20, because that is where you gave your input, right? So x slash wx of So if you start here, you will get to see what happens from RBP minus 0x20 up until RBP minus 0x4. So here, if you actually start from RBP minus 0x21, you can see that this is where it started. 20 is where it started. Before that, it's just null bytes. So again, going back to RBP minus 0x20, 4, 4, 4, 4, 4, 4. How many times? 4 eights are... Yeah, 7, 4 sevens are 28. Sorry, yeah, 28, and 28 bytes of after 28 bytes of 61s, you have actually given 0x cafe babe, and this is where the check variable is. So if I have to show it to you explicitly, like x slash wx of RBP minus 0x4, yeah, it's cafe babe, and it's the same space. So it's just an internal of the 64-bit systems that when you actually work with 64-bit systems, it actually always allocates at least 8 bytes of space to a variable. Is that clear now?
It's more clear. Thank
Yeah. Any other questions? I can move on to the next slide, I guess then. Are you sure there are no more questions? Okay, moving on. Applications of binary exploitation. So these are not the only exploitation applications, but these are the two I can tell you right now. Like there is kernel exploitation. So the bugs that we have found right now are all in the user land. So at max, what you can do is you can access my file system and just remove my files, or just view my files. Maybe I don't think you can remove them. Yeah, you can probably remove them too if with some other permissions. But yeah, so if you have such bugs, you can access my files, and that's the most you can do with it. So it can be worse if the bug is found in someone's kernel, and if that is exploitable, the entire OS is actually at stake. Like the whole kernel, like everything works with the kernel, right? So if the kernel has been exploited, everything is gone, and you might not be able to access your own files. So that's the extent of uh, tragedy that kernel exploitation can cause. And then browser exploitation, we might all be familiar with browser exploitation, because browser if a browser has a malicious code, and if a browser can do various things, like it can actually execute and download files into your file system, and if our browser is exploited, it's like almost our entire system is exploited. So these two examples are like very popular now, because and are very much in research right now. So there are a lot more examples which you can all go through, like research yourself and find out. And I can definitely give you resources later on. I'll put it on Discord. So that's the end of the talk here. So thank you for listening, and hope you understood what I was trying to tell you. If not, you can always ask your doubts now. I'm still here.
Thank you very much.
Yeah, you're welcome.
Yeah, I just would like to add some additional notes that if you are like a pure beginner and you did not understand most parts of it, that's totally okay. Because yeah, there, even though it's a beginner in binary exploitation, there is already few stuff which you should be a little bit familiar, like the hex notations, or how the assembly looks like. And yeah, in the demo she showed, she's already going fast with debuggers. But yeah, if you are like a pure beginner, the key takeaway that you can have from here is that yeah, there is a tool like GDP Beta which you could try to use, and there is yeah, how there is a structure called stack in the memory, and there is a call function, and you can push and pop stuff out of it. And if you only, even if you remember just these key words, that it's already good. And then that could be a starter for you to just get started with searching for these. And there is so much resources out there in the internet where you can search for and try to find more information. And yeah, the goal is also that you can start at some point. You should start trying on your own. That's only when you have the real learning. So it really takes time, and you have to take a look at it in your own speed, because at the speed, if you are a beginner, it's not very easy to grasp so many new things. So just yeah, go over everything at your speed, the slides. And please ask questions in our discussion channels in Discord, and we will be very happy to help. So yeah, please do that, and we will try our best to support in whatever ways possible.
Okay, if you have doubts, you can still ask. If not, you can fill out the feedback form, and the link is shared in the chat right now. And I forgot. Like there are a set of challenges on Traboda that we have uploaded like a few days back, like for seeing this training. So if you are on Traboda, if you don't have an account yet, please go register to our contest. Uh, yeah, the link is in the chat now, so you can register and create an account and then participate in the contest. Please use this link and don't just go to traboda.com. You have to find out this contest and then register to that, and you can check out the challenges. And it these all like very simple challenges are there, so you can all try it out. And hope you had fun. Thank you.
Hey, stop the recording.
Yeah.